Good morning, afternoon, or evening, depending on the geographical coordinate you are in around the world. My name is O.A. Adeleke. This is EEE 231 class, Engineering Analysis. The topic we have today is calculus. Differential calculus, to be specific. Calculus is a branch of mathematics that deals with finding the different properties of integrals and derivatives of functions. It is based on the summation of the infinitesimal differences. Calculus is a study of continuous change of a function or its rate of change. It has two major branches, as I mentioned earlier, differential calculus and integral calculus. Differential calculus, same as differentiation, this deals with the rate of change of one quantity with respect to another. For example, the rate of change of current with respect to time, the rate of change of distance with respect to time, or the rate of change of velocity with respect to time. It can even be the rate of change of flow of water through a pipe per time. You can consider it as a study of rates or different quantities. Still in differential calculus, for example, you know about velocity, which is the rate of change of distance with respect to time in a particular direction. That is, if f of x is a function, then f prime of x is equal to the dy dx. That is the differential of x or derivative of x. When you differentiate y as a function with respect to x, we say f prime of x is equal to dy dx. Now talk about derivatives. Look at, for example, now y equals f of x. The slope formula is that the y over the x, that is changing y over changing x. Increase in y, in other words, over increase in x. On the y-axis, the difference between, let's say, y1 and y2 over the difference between x1 and x2. That's what we're talking about, the slope. And look at this, looking at this diagram, you can see the y, you can see the x. So changes from x to x plus dx, and changes f of x to f of x dx, as you can see in this figure. Now, look at that. This is trying to explain differentiation to us from the first principle. Differentiation is what every one of us is aware of from our earlier days as engineering students. Even as science students at secondary schools, we at least, more or less, we have been used to differentiation. So we're just trying to recover, just to remind us and to apply differentiation to solving engineering problems or engineering issues. Now, for example, look at f of x equals x squared. We all know that f of x equals x squared. Then you differentiate f of x equals x squared. We have f prime of x to be equals to 2x. Just something that we know. That is dy dx as limit approaches 0 is equal to dy, the capital D over the capital D, dy over the capital dx, called dy dx as limit of x approaches 0, it becomes f prime of x, that is dy. That is the slope of the function f of x. All this is just trying to tell us from the first principle how we can differentiate the function f of x. That is the same thing we are trying to say. To the notation, d dx of x squared is equal to x. The derivative of x squared equals 2x, or simply d dx of x squared equals to x. Just trying to refresh our memory to what we already know. Now, if you now say d dx of x squared, where x squared is equal to f of x, equals 2x, what does it actually mean? It means that looking at this graph, the graph here is the graph f of x equals x squared. What we mean is that for the function f of x, that is x squared, the slope or the rate of change at any point on this graph, you can see, any point on this graph, the slope is 2x. That is to say, depending on the particular point. So when x is equal to 2, the slope is equal to 4, or when it's equal to 5, the slope is equal to 10. Then at different points of the curve, the slope, the y dx of x squared, is equal to 2x. That's what we're trying to say. And also say it's not limited to x. It can be t squared depending on what you are differentiating with respect to. We can differentiate with respect to t. We can differentiate with respect to q. We can differentiate with respect to x. It depends on what you are differentiating with respect to, as we see when we solve some engineering problem. The same way, if it's no more x squared, if you have x cubed, no, the derivative of x cubed is 3x squared. This is just also trying to differentiate from the first principle. F prime of x, where x is equal to, well, f of x is equal to x cubed, is equal to 3x squared. That is what we are saying there. Now, this just notation. What's notation? How do we represent? How do we show? How do we write it in notation forms? F of x, f prime of x, limit as just produce 0 is f prime x plus dx minus f of x over d of x dx. That is f prime of x is equal to dy dx. Now going straight to what we actually want to do, you have established how to differentiate f of x on the first principle. Now going straight to what are the approaches, what are the techniques or the methods we use in differentiation or in solving differential calculus problems. First is a function of a function. Function of a function. That is, a function is in another function. This function is dependent on another function. The function of a function. If you look at this, if y equals f of u and u equals f of x, that is to say, u is a function and is a function of y. For example, if y equals sine of x squared, sine x squared, find dy dx. In that case, we have y equals sine x squared. That y can be said to be f of u, and then the x squared there can be u. That's what I'm saying. So u equals x squared and y equals sine u. And this is the formula for solving it. Maybe if we have a function of function, y equals f of u and u equals f of x, we have dy dx to be dy du multiplied by du dx. So if y equals sine x squared, find dy dx, u equals x squared, u equals x squared, and y equals sine u. From here, we know that u dx is 2x, while dy du here is cos u. Something that you know when the derivative of sine u equals cos u. So look at that. And so dy dx is where dy du multiply du dx. That is to say 2x multiply cos u. And u is this. U is x squared. So 2x multiplied by cos x squared. That's the dy dx of y equals sine x squared. That's an example of function of function. Function of a function within another function. That's how to solve it. The next is the product rule. Product rule. If y equals uv, that two functions are multiplying each other. Y equals uv, where u and v are functions of x. That is u of x, and then v of x. In other words, you can say u equals f of x, v also equals v equals f of x, u also is equal to f of x, or v of x and then v of x. Both v and u are functions of x. In that case, dy dx is u dv dx plus v du dx. Look at an example. We have this, y equals exponential 2x multiplied by sine 4x. We are supposed to find f dy dx. You get? So that is all you can see the way I'm writing it here. So if u equals e of 2x and v equals sine of 4x, this is a direct product. Two functions multiplying each other. That is exponential 2x and sine of 4x. Like that. We apply this formula. We are going to arrive at this as the solution to that problem. Now, look at the other rule. We have talked about function of function. We are talking about product rule. The next to talk about is quotient rule. Quotient rule. That is when we have a numerator and a denominator. That is, u equals f of x and v is also f of x. So for y equals u of x over v of x, that is, v is dividing u of x. That is what do you call it? That is fraction. That's quotient. So formula for that is this: v du dx minus u dv dx all over v squared. And look at an example. If y equals x to the power 4 over x plus 1 squared, you have to find dy dx, find y prime of x, find dy dx. That's what we have here. U equals x to the power 4 and v equals x plus 1 all squared. If you solve this using this formula, we are going to have this as the solution to that problem using the quotient rule. Using the quotient rule. The next rule here, the next one we are dealing with is the implicit function. I would like you to pay good attention to implicit function. Implicit function. When we have two variables x and y that are related or that are inseparably related, you understand? We have an implicit function. Mind you, I said y equals f of x, the original conventional problem in soft differentiation. We are differentiating with respect to x. Differentiating with respect to x. But if we have an implicit function, there are two variables there that are joined together, and you cannot just separate them to differentiate them individually. So you must differentiate them implicitly. For example, look at this function. If x squared plus y squared minus 2x plus 2y equals 23, find the y dx, find the squared y dx squared at minus 2 and 3. At minus 2, that's at x equals minus 2, and as y equals 3. This is solution to that. Solution x squared plus y squared minus 2x plus 2y. Look at it now. Look at the first one. This solution to this problem. X squared. Differentiate x squared straight, it is 2x from what we know. But because this y is a stranger, we cannot differentiate y with respect to y. That is why differentiating v will give us 2y dy dx. Because our differentiation is usually with respect to x, but we have a y. So it has to be 2y dy dx. This one, and then minus 2. This is 2x. This is 2x. Differentiating 2x, it gives us 2. Because in fact, that is in terms of x. Then the other one is 2y. Because there is also a y, it is 2 dy dx. From there, we bring the common terms together. We have 2y plus 2 dy dx equals 2 minus 2x. That gives us this particular solution here. And then at minus 2 and 3, we give us this value. Now, the squared y dx squared, we are differentiating our answer. We are differentiating this one, this dy dx. We are differentiating it the second time. That gives us this squared y dx squared. Look at it. This is bringing us into another technique. This is the quotient rule we are going to make use of here, because this is u of x and this is v of x. So applying the quotient rule for this one, give us the second derivative of the problem we are solving, and that gives us this. Using minus 2 and 3, so imputing minus 2 and 3 will give us this value, 25 over 64, as the second derivative at coordinates minus 2 and 3 of our given problem. All right, that is for implicit. The next technique is logarithmic differentiation. Logarithmics, differentiation of logarithmic terms involving functions involving logarithms or exponentials. If I look at this example, if y equals this, cos 2x over e exponential 2x, find dy dx. Now, this solution to that, when you're solving a logarithmic problem, we have this. You find a natural logarithm ln of y. This is how to solve this problem from beginning up to the end here. Going through, you can see it's so straightforward. This can see here we have logarithmic, we have function of function. This function of function here, they can be ln u. Then this is ln u. This can be 3x plus 1 can be u. Then ln u. Then the cos 2x can be u. Then we have ln u. Then this exponential function, and then differentiating it 1 over y, because this is what? This is implicit. We can see function of function, we can see implicit, and we can see logarithmic. These are three different techniques coming together in this particular problem. You can see this is ln y. It is not x. That's a 1 over y dy dx. And solving it, we give us this final as our answer. Now, the next thing I want to briefly talk about are the applications of differentiation. I mentioned at the beginning of this course that this is just engineering mathematics. It is engineering analysis. Engineering analysis. That every one of us, we learn how to apply differentiation. We learn how to apply calculus to diverse engineering problems, be it electrical, be it mechanical, be it food engineering, be it computer, be it agric, or be it chemical engineering. We learn how to solve engineering problems, making use of calculus techniques, differentiation techniques. For example, now this is one. Look at the equation of a straight line. That's the very first application area of differentiation. You can see y equals mx plus c, where m is equal to slope and c is the intercept on the y-axis, as we all know. So m equals dy dx, as we said before. M, which is slope, is the increase in y over increase in x, or directly talking about it, dy over dx. But now that is the equation of a straight line normally. But if two lines are involved, that is to say, we have two lines on the Cartesian plane, y equals m1 plus x plus c, and y equals m2x plus c for the two lines. Well, the first line is having a slope of m1, the second line having a slope of m2. Now, if m1 multiplied by m2 equals -1, or that is to say, if m2 equals the inverse or negative inverse of m1, that is m2 equals -1 over m1, then the two lines are perpendicular to each other. Please note these conditions. You could be asked in any form to justify or otherwise that the perpendicularity of two straight lines is mean unity or negative unity. If you can see, if m1 times m2 equals -1, then the two lines having the slopes m1 and m2 are perpendicular or orthogonal to each other. Now also, if the two lines are parallel, the m1 equals m2. Two parallel lines don't meet. So if that means the same increase in y will happen for the two lines, and same increase in x will happen two lines. That means to say the slopes of two parallel lines are usually equal. Take note of that. That's a very strong application area of differential calculus, equations of straight lines. Now, another thing, apart from straight line, we could have curves. But when we have y equals f of x may not necessarily be a straight line. It could be a curve. For example, if f of x is involving exponential, is involving power, then we are not talking about straight line anymore. We are talking about curves. Now, if you have a curve, we need to have look at tangent to that particular curve. Look at this figure, y and x. There's a curve. The curve here is y equals f of x, and there's a tangent drawn touching the line at P. The slope of y equals f of x at point P is given by the slope of the tangent to the curve at P. What they're saying is, for this particular curve, the slope of that, the slope of the line of this curve, y equals f of x at P, is the slope of the tangent to that curve at P. That is, the tangent is a line drawn that just barely touches the curve at a particular point. So the normal to the curve will also have a slope, which is the inverse of the slope of y equals f of x at P. Just take note of that definition. Now, example 1. Looking at that, we've said we have used the differential calculus to explain equation of a straight line. We are now using the same differential calculus to explain the equation of a curve. I'm talking about tangent and normal to a curve. Look at this. A curve is given by 4x cubed plus 4xy plus y squared equal to 23. As you can see, this equation itself is already telling us it's an implicit function. It's an implicit function. I'm going to use an implicit function technique to solve it, to get the derivative. So if this is the curve, find the equation of the tangent and the equation of the normal to the curve at 0 and 2, at point 0 and point 2. Solution. You can see it's an implicit function, so we solve it. We solve it implicitly by that, like that. We have the y dx to be this. Recall the way we solve implicit function. So at this point 0 and 2, we have the y dx to be -8/4. That is -2. Now, from equation of the line, now mind you, this is not the end. This is not the end of this. Okay, this is not the end of this. We have equation of a line that we have -2. This is what we got before. M equals -2 gives us this. This is another way of writing equation of a line. Y minus y1 equals m into x minus x1, where we have two separate coordinates, x1 and x1 and y1. So we have this y minus 2 equals -2x. This y equals 2 minus 2x is the equation of the tangent. However, slope of the normal is the minus of the inverse of the first slope. That is -1 over m1. That's the slope of the normal. That's -1 over m. For that particular line, the normal to the curve, we first get the slope. After getting the slope, we now get the equation of the normal. The equation of the normal is this, while the equation of the tangent is the one here. So these are just two application areas of using differential calculus in engineering, in mechanics, especially because they're dealing with equation of a line, equation of a line, equation of a tangent, equation of the normal. We are talking about mechanics in the real sense of the word. So we are still going to have more examples, more application areas of differential calculus in our next class. But at this time, I will say I will stop. I will stop now, and then I will see you again in the next class. Take care. Have a wonderful day.